All right. Hello. Welcome to the Valentine's Day edition of Off by One Stream. Um, but really excited for the stream. We've got Connor McGar on, and he's been on the channel before. I think it's probably been over a year, I think, the last time you were on, right?
Yeah, so I think November of 2022 or three, something like that.
Yeah, it's been a while. Yeah, it was definitely one of the more technical streams. So everybody expects big things out of you, Connor. So no, Connor came out and spoke at Hackfest again in Hollywood this past October and did another great talk. And he's got a lot of the same interest I do around exploit mitigations and reversing and debugging them to understand their effectiveness and workarounds and all that fun stuff. Because obviously, the more you understand around about the mitigations, the more time you can focus on the things that you know will actually work. But I guess, Connor, for those who don't know you, you want to give a little background about yourself?
Yeah, so as Steve said, my name is Connor. I work at a security startup called Prelude Security, doing some interesting research, just overall security research. Before that, I was working in CrowdStrike. I was working in the product org, working on EDR features, things such as that. And previous to that, I was in the customer-facing red team, which most people are surprised to hear that CrowdStrike has one of those. So I'm just primarily interested in anything relating to Windows internal, C, assembly, debuggers, anything like that. And yeah, that's pretty much it about me.
Do it. Thanks. Yeah, Connor, one thing I'll say for those of you who may not be familiar with Connor, he's one of the, I don't know where he gets his time because he's one of the nicest people in security you can talk to in the research space where he helps a lot of people. Like people have complex problems and he's very, very generous with his time and giving tips and advice to people and some amazing blogs that he's published. I will post the links to those as well. Of course, most recently was the one on the Windows kernel mode shadow stacks, which is going to be the topic for today. But there was another great one I remember on, I believe it was a V8 issue or X. That is why I have a backup internet connection. So are you still there, Connor?
Yeah, I'm here. Okay.
Yeah, so basically I have two, fiber lines and it's windy on the top of the hill where I live in Berkeley. So one always tends to go down. So I just have to fail over to the other one. So sorry for that.
Yeah,
I
no
don't know if you got
worries.
my question or not.
I heard something about V8 and then that was it.
Yeah, I was saying one of your papers was really great. I believe it was on exploiting a Chrome vulnerability in V8, right? With the JIT code and the CFG bypass.
Yeah, so it wasn't V8, it was actually Edge when it was still on the Chakra engine.
Right.
So I always like to joke with people that, in my opinion, that was probably one of the most secure browsers that existed. And it's kind of sad to see it go, but yeah.
Yeah, I mean, that was a big risk for Microsoft to change Internet Explorer finally over to a new browser name in general. I don't know if that had anything to do with it, but obviously it got a bad reputation for the monthly use after free and type confusion bugs ranging around 40 to 60 per month, which is pretty crazy.
Yeah, no, the Internet Explorer was pretty interesting, but yeah, I really like the old Edge when it first came out. I found it very interesting.
Yeah, totally. Cool. Let me start off with a couple of questions for you, and then
Okay.
I'm sure going to be answering a lot of these. So if I ask a question and you say, yeah, I'm going to cover that, then we'll just move on to the next one. As usual, for those of you watching, please feel free to post any questions. While Connor is obviously presenting and in the technical depths of doing something, I'm not going to interrupt, of course, but we'll get to your questions at the end, if not before or during that portion. But I know you're going to cover this one, so I'm not going to ask it. Oh, this is a good one. Are shadow stacks on by default now in Windows 11, the latest versions? And if so, is it only in the kernel or is it user space too while the processors catch up, or you know what the state is?
Yeah, so I don't think that it's enabled by default. I think that for specifically kernel mode shadow stacks, someone will definitely have to correct me, but I'm almost positive it's on one of the versions of Windows 11 is when support began. It could have been available earlier, but it was through an undocumented registry key, which obviously it's still done through the registry key. But for a while, a few versions of Windows 11 ago, I think maybe as of like November 23, something like that, there was a toggle in the UI for the Windows Security Center where you could enable kernel mode shadow stacks. For user mode, it's something that you have to enable on a per process base, so you have to compile in support for it. And I don't think that it's just enabled by default. It's like a kind of blanket feature. I think it's going to depend on whatever uh, compilation settings you have. And then for kernel mode shadow stacks, which we'll get into, it requires HVCI being turned on.
Yeah, I think it was a Tiger Lake CPU for Intel anyway, was the first one to support it. So there's still a lot of obviously laptops and equipment out there that just don't have the spec yet. Cool. I guess you might talk about this one, so we can skip it if you want. But have there been any workarounds that are reliable that have been published or that you've seen or discovered?
For like shadow stack quote unquote bypasses, I'm guessing it's relating to. I've seen some online. There's kind of two methodology. Well, really, there's one methodology for what I've seen, and it doesn't come down to attacking the mitigation directly, like, oh, there's some weakness. It's more like, let's move over to some other primitive. So I've seen something called counterfeit object-oriented programming, which can be used to circumvent kernel CET specifically. But most of the time what I see is CET has two features, the shadow stack and then something called indirect branch tracking. Windows does not employ indirect branch tracking because the control flow guard feature is used instead. So most of the research of what I've seen is more just outlining, hey, don't try to fight CET with shadow stacks, just try to bypass control flow guard. And it's not that control flow guard inherently is flawed, I guess you could say, in a sense. These are known limitations, right? Like control flow guard works by allowing, there's this bitmap of all of the known indirect function calls used at compile time. And all CFG does is it goes, hey, when this indirect call is about to happen, do I know about this function in this bitmap? It does not say, hey, I'm about to call this function, make sure it's the function the developer intended. So that's not like CFG is bad. That's always been a known limitation. It's got an open fail kind of policy surrounding it. So that's more of what I've seen. That was going to get thwarted with the advent of something called extended control flow guard, or XFG, but it seems that that's been deprecated thus far. So they're still basically just CFG. So most of what I've seen is just target CFG instead.
Yeah, do you remember the boundary alignment for that, for the bitmap? It's like 1K or 4K or something?
If you're talking about like the bitmap, there's something in there that all functions should be hex 10 byte aligned. So there's basically part of it is when the bitmap is checked, that's an implicit kind of rule. Like if you're calling into something that's not 10 byte aligned, we don't even really need to check any further because all of the functions should be aligned. So that's one kind of optimization that's made in the bitmap.
Yeah, I remember using the tool Ropper before from Sasha Shira, and somebody wrote an extension for it that gets you the ROP gadgets that still work with
exactly. Those just have to be hex 10 byte aligned. Yep.
Yeah. Cool. Do you think this will work? Like, do you think shadow stacks? I remember Alex Ionescu and Yarden Shafir released that paper a couple of years back saying CET and shadow stacks, the death of ROP or something like that. Do you see that this, when fully implemented, will that be the end of like stack-based buffer overflows and return-oriented programming?
I hate using definitives in security, but what the shadow stack feature does is it mitigates ROM. Like if it works the way that it's intended, I haven't really spent much time into the how do I bypass this or that sort of thing. It's more, these are complex features. The implementation, especially like kernel CET, at least in my opinion, right? Like I'm a novice, I'm still figuring this stuff out. It's pretty dense. So like it's hard to say, but I haven't looked too much into the how do we bypass that. Again, most of what I've seen in the research that is out there, I think Yarden did a talk at Offensive Con, which more showed how you can get around CET by looking at some of the known limitations of the mitigation itself, specifically for user mode. But I haven't looked too deep into that. But for what CET says it does, and like from what I've seen, yeah, it's going to thwart stack-based buffer overflows and ROB, just because if you're using a stack-based buffer overflow, you're trying to corrupt a return address on the stack. That's exactly what CET, shadow stack specifically, is meant to mitigate.
Yep, perfect. This next question, and Hussam just asked pretty much a similar question, so I'll just ask them together. What do you see the future of kernel mode exploitation looking like with HVCI, VBS, whatever, and how would micro virtualization change the game at all?
Yeah, so I've mentioned this before, and I think it's kind of just a commonality in the vulnerability research world in general. You see a lot more folks moving to data-only style attacks. So for those who are unfamiliar, what that does not mean is that memory is not corrupted. Memory still gets corrupted. You're corrupting metadata of objects or forcing weird things to happen. You're just not doing it in a way that allows you to execute foreign unsigned code on a machine. So an example of this is it's mitigated now, but every thread object managed by the kernel in Windows is known as a K-thread object. It manages, here's the stack limits of the thread. Here's, the X state features, that sort of stuff about the thread. There's a flag in there called previous mode, which denotes because on Windows, when you do a system call, it's issued in context of the thread which issues the system call, generally speaking. And so with that, threads actually have two stacks, which we'll get into a little bit with the CET demo stuff. It's got a user mode stack, it's got a kernel mode stack. So that previous mode flag denotes when a system call is issued, the thread that's issuing it, where did it come from? Was it a kernel caller or a user mode caller? What you can do is, corrupt that flag. It's documented everywhere. It's like one of the most popular exploit techniques that is out there. You can corrupt the previous mode flag to say, hey, this thread actually is a kernel caller instead of a user mode caller. And that allows you to bypass certain checks that the kernel will do, right to kernel mode memory, etc. So you see how that isn't an unsigned code execution, kind of traditional ROT-based, call virtual protect, make the stack writable, or executable, and jump to the shellcode. You're kind of corrupting the metadata that's there. You're not inherently changing permissions or doing sketchy things. Those are things that VBS doesn't necessarily care about. And that's, again, not a fault to VBS or HVCI. It's a known thing. It's like we are directly looking at, HVCI is called hypervisor protected code integrity, right? It's not hypervisor protected data integrity. So that's more of what folks are moving to and will continue to move to. The most classic example of this is overriding processes token with the address of a token from a privileged process. That's like one of the oldest techniques that's out there. That's actually a data-only attack. Now, a lot of people do this in a way that they execute shellcode in order to do that, but you can do that all through just a read-write primitive. So that's more of what folks are going to move to. It's not about trying to fight the primitives. It's choosing the path of least resistance. And data-only attacks are things that are harder to detect.
Yeah, it's funny you bring up the token stealing from the system process. When David Weston was at Hackfest, first thing I did was corner him. I was like, I got several questions for you, dude. I was like, one, why is that still possible? Why have you not found a way to protect the system's token? And another one was like, why did you guys choose the invasive method for smart pointers on C++? Because that's what allows us to do the exploits against the browser all these years and stuff historically. So it's nice when you get somebody like that, you can finally get the answers to your questions.
Yeah, exactly.
Cool. I'll save other ones for later. I know you got a lot to show, so if you want to go ahead and share your screen, we can get started, and I'll let you run.
Yeah, so I'll just say I'm prepared as best I can in the amount of time. So you know, I'm going to do the best, but I'm going to break this up into two segments basically. One is talking about, you know, just virtualization-based security in general. And then the other is kernel mode shadow stacks. And the reason for that being is you actually need HVCI to be enabled for kernel mode shadow stacks to even be enabled. If HVCI is not enabled, you're not going to get the benefits of the CET shadow stack. So I'll just share my screen now and kind of talk about, you know, for those unfamiliar, what that entails. So let me go ahead and start sharing this. And this is just going to be a paint window for now, just and then I'll switch to the debugger and whatnot. But you know, if folks are not familiar, nowadays on Windows, you have a suite of features under the umbrella of something called the virtualization-based security. And what this is Windows effectively runs in a VM. Now, again, if you understand this at a more technical level, that's not entirely true, right? You don't have the virtualization of the network stack and, you know, video cards and all this stuff. The overarching concepts of virtualization are used. And so the way this works is Hyper-V is Microsoft hypervisor. So you can think of, you have, you know, your computer, right? This is my PC. And inside this PC is, you know, Windows. So traditionally what would happen is Windows would just be installed on your hard drive, and Windows would take up the what we would call, you know, partitions, so to speak. And then every time you wanted to create a VM, what Hyper-V would do is partition out physical memory for each VM. So you have VM1, VM2, etc. But you would still have the presence of Windows there. What happens now on Windows is you have something called virtual trust levels. And virtual trust levels are effectively your VM, so to speak. So on the PC itself, you have something called the root partition. That's just all of the physical memory, so to speak. Again, I'm simplifying some of this stuff. So within that root partition, instead of allocating how we did previously, specific partitions, so VM1 is in, you know, partition 1. VM2 is in partition 2. Again, simplification. Partition 3 for these VMs. What happens now is these things called virtual trust levels are all present in the root partition itself. So we can take this away and type in root partition. So now we have VTL 1 and VTL 0. And they're both located in the root partition. All of VTL is a specific set of access rights on physical memory. So the root partition has access to all of the physical memory. VTL1 has access to all the physical memory. VTL0 has access to all of the physical memory. And VTL0, this is where your typical NTOS kernel and typical user mode code is. VTL1, you have something now called the secure kernel and isolated user mode. And what happens now is when the system is booting up, we no longer just, again, I'm simplifying a lot here. We don't just boot into Windows how we historically did. What we do is we give the secure kernel, as boot is happening, a chance to actually configure VTL0 as it sees fit. So secure kernel is able to configure VTL0 as it wants. Most notably, this comes in the form of configuring the actual physical memory for this VTL. VTLs are treated as VMs, as I mentioned. They're not VMs in the sense of, like I said, they've got all of this, they've got their own interface from like a graphics perspective. Like you can have Windows 1 VM over here, Windows 2 VM over here. That's not really how it works. Again, what virtualization-based security does is uses the concepts of virtualization to perform this isolation. It doesn't necessarily do the exact same thing as creating a new virtual machine. And so what happens is you have something known. Let me go ahead and just erase all this. So before I erase all this, what happens now is you have two VTLs in the physical memory of Windows. You have VTL1, which is secure world. You have VTL0, which is normal world. Whenever you're interfacing with Windows, using Microsoft Word or the browser or what have you, you're interfacing with VTL0. VTL1 is not directly transparent to the end user, so to speak. And so what happens is we use the concepts of virtualization to allow VTL1 to configure VTL0 as it sees fit. So on Windows, the way that something called virtual memory works is it's an abstraction of physical memory. So virtual memory allows the OS to effectively think it has access to a lot more memory than it actually does itself. And the way this manifests itself is through something called page tables. So on Windows, you have these on 64-bit systems, on something called long page mode, just typical paging, you have these four paging structures. PML4, PDP, PT, and PT. And what happens is every process has its own set of page tables. So anytime you create a process on Windows, a set of page tables is assigned to it. This is how the isolation or the per process private address space works on Windows. And so what happens is every process object, so let's say this is process 1. There's something called the K process object. And it contains a field in the object itself that has the physical address of the base, the root of the page table. So let's say in this case it's 0x1000 physical. And you may have heard something called a context switch on Windows. So what happens is when execution needs to start occurring in context of a specific process, there's a special CPU register called the CR3 register. When that context switch happens, the process's root page tables get loaded into this CR3 register. So this is where you can always find the root of the page tables. And what happens is the CR3 register, this base paging address, is used to index every page table like this, and like this, until a final address, like our virtual address, is outputted. So I'll share my debugger in a second to explain this. So you have your base of the page tables, and that is used to locate the next page table in line. That is used to locate the next page table in line, and so on and so forth. And all of virtual addresses, so let's say you have this virtual address right here, VA of 0x7FF, 1, 2, 3. I don't even think that's a canonical address, but let's just say for the sake of it. All of virtual addresses is when you break this address down into the binary, into the actual bits, it contains the necessary indexes for each of these indexes into the next page table. So the first couple of bits of the virtual address for the current process's page table says, hey, here's where you can locate the page directory pointer for this memory address. Here's where you need to go to find it. The next set of bits of the virtual address says, here's where you go to find the page directory. The next set of bits, the page table, and the last set of bits, an offset. So on Windows, most page operations are page aligned, and so it's the offset to the page itself. So all this to say, virtual address 7FF1122334 is associated with the page tables for this process 1. Process 2 may have this same virtual address, but again, the page tables associated with that process are different. Processes 2 page tables may start at 2000 like this. So when you perform this index into these page tables, so to speak, the contents are going to be different. This is what allows the per process address space isolation on Windows, right? This exact same concept can be used, in fact, is used, if you think about it conceptually, is used to isolate the virtual trust levels with virtualization-based security. So in virtualization, you have something called a guest physical address. Let's do GPA. So let's say I have a computer and I have a VM running right here. Inside this VM, you're going to have memory access, just like on any computer. A VM is just, a computer within a computer, so to speak. So virtual machine 1 is going to go access what it thinks is, let's say, 0x7FF11. Oops. 1, 1, 2, 2, 3, 3, 4. Again, this may not even be a canonical address. But when it goes to access 7FF11223344, it's doing it in context of this virtual machine. This address does not necessarily exist on the physical machine itself. Right? So memory access is only done in context of this virtual machine. So what happens is 7FF11223344, we know has to be converted into a physical address on the physical machine because that's how virtual addresses work. They all are associated with a physical address. So what actually happens is the VM produces something called as an intermediary address, this guest physical page. So VM1 goes to access 7FF11223344. In context of the VM, this gets converted into a physical address. Then you have the system physical addresses. These are the actual physical memory of this entire computer. Because again, if we think about it logically, if this large box on the outside is the actual computer itself, we know VM1 is still using the physical memory, right? So this is physical address 1, this is physical address 2, this is physical address 3 and 4, let's say. So this is 1000, 2000, 3000, 4000. So this VM, again, this is very contrived. It wouldn't be exactly contiguous like this, but this VM can be found in addresses 2000, 3000, and 4000 of the actual physical memory itself. But then VM1 is going to have what it thinks is 1000. What it thinks is 2000, what it thinks is 3000. So if you look here, VM1, if it goes to access physical address 2000, this is probably, let's actually make these 2000, 3000, 4000. So when VM1 goes to access physical address 3000 right here, it's actually located at 2000 on the physical machine itself. This is what the guest physical address is used. It contains all of the necessary information to convert this 3000 into this 2000 right here. And so this allows isolation of the address space because the VM doesn't know that it's a VM in the sense of when it goes to access a physical address, it doesn't know that it's a guest physical address. The hypervisor itself is what provides this functionality. So just as each process is associated with a set of page tables, which perform the per process address space isolation, each VM is associated with a set of guest physical pages. And these are maintained through something known as the extended page tables. So you have something known as second layer address translation. That's the technology which facilitates this. Intel's implementation of extended page tables is known, or excuse me, of SLAT is known as extended page tables. So again, VM1, it can access this virtual address all that it likes, but that gets shipped off to the hypervisor, and the hypervisor is responsible for determining which physical address we go to. So why do we care about any of this at all? And again, if folks have questions or whatnot like that, please let me know. This is like,
no, everything's good.
Stuff. Yeah.
I was just telling them they're lucky we don't have to go to PML5 yet. So
yeah. So let's go back to the VTL example. So this is root partition, VTL 0, VTL 1. This is normal world. This is secure world. So let's say that VTL 0 goes to access this address 7F, F, 1, 2, 3, 4, 5, 7, 8, 0, 0, 0, 0, 0, 0, sign extended. K-user shared data as an example. When VTL1 actually goes to access this kernel mode address, it is not allowed to just directly access it because VTL1 is treated as a VM, just like a guest is. So how does a VM, what happens when a VM goes to access a virtual address? It doesn't just directly get the contents. It first goes to find the guest physical address of this virtual address. And then that gets converted into the system physical address. So all this to say, anytime VTL 0 goes to access virtual memory, this is gated through a guest physical address intermediary address. So I mentioned earlier, VTL1, as the system is booting, I said it is allowed to configure VTL 0. The way that it actually works is it is allowed to configure the guest physical pages for VTL 0. It can configure the extended page tables for VTL 0. So you can do a lot of cool things. VTL 1 can set permissions on physical memory. Again, these are guest physical pages. It's not setting the permissions on virtual memory. It's doing it at the actual physical level. So it can set permissions on physical memory, and it can say, as an example, let's take, I'm going to erase just a little bit of this and move this over. So let's say we have address 0x, or let's do this in black. Okay. Let's say we have physical address 0x1000. Since VTL1 is able to configure the permissions for 0x1000, VTL1 can do some interesting things. VTL1 can say 0x1000 and VTL0 should be readable and writable. VTL1 could say 0x1000 and VTL1 is writable, read, write, execute. Now, that would never happen because you don't want to create read, write, X memory, but it could if it wanted to. A better example of this is VTL1, VTL0. VTL1 could say this is a readable, a writable, and a valid page in context of VTL0 or VTL1. But it could say actually this physical page is not even valid in VTL0. So even if you try to go access the underlying physical memory under the hood, that's not the end-all be-all answer, because VTL1 configured the guest physical page to say 0x1000 should never be valid in context of VTL0. So if VTL0 wants to make that page valid in context of itself, it would have to corrupt the guest physical address or the extended page table entry. Well, that extended page table entry is managed by the hypervisor. So we now have this privilege setup where before you had user mode and kernel mode. Once you're in kernel mode, it's game over. You have access to the page tables, all of that stuff. But now you have an additional layer. You have your kernel mode, but then you have the hypervisor. The kernel mode cannot just access the hypervisor, just like a VM can't just arbitrarily access the extended page table entries, right? So VTL0, if it wanted to make this page valid, it would have to do something called a hypercall, which is like a system call, so to speak, to ask the hypervisor to make that page valid. So all this to say, it does not matter at all what the page table entries say in VTL0. So I'm going to stop sharing this screen for a second. Hopefully all that makes sense, and I'm going to open up the debugger.
Hey, you're taking me back to an old VMware interview I had.
Oh, nice. So, Steve, is this text big enough? I've zoomed in a little bit.
It's very, very small on the top. The bottom's fine.
Yeah,
like the log window. Yeah.
Yeah, that's fine. I just need the bottom for now.
Okay.
So let's say 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right. So this is K user shared data. So if I do this is the actual structure itself. So if we parse it as a K user shared data structure, we can see, oh, NT system root, C Windows. Okay, everything's being parsed properly. This page says that it's kernel mode, readable, and valid. If I took this page table entry, just like this, and I corrupted the page table entry. Again, these are the normal page table entries. These page table entries are what are used to produce the guest physical address. And then the extended page tables are used to convert that guest physical address into a system physical address. So when a VM is operating on memory, it's using its quote unquote traditional page tables in order to fetch that physical address. And then the guest physical address is what's emitted. The extended page tables are used to locate the actual system physical memory. Okay. So if I corrupted this page table entry and I made this page kernel mode readable, writable, and executable, and then went to go execute it, my system would crash. The reason for this being is because my VM has HVCI enabled. When you have HVCI enabled and you go, your machine is running as a quote unquote VM. So when I go to execute memory, what happens? The memory needs to first get converted into a physical address because we need the actual physical contents. It's unbeknownst to the user because the CPU operates on virtual memory, but it happens under the hood. And then that physical memory, we get the contents from, so to speak. Well, we no longer trust these page tables, the traditional page tables. So anytime execution happens, the extended page tables are the source of truth because these page tables are located in kernel mode. An attacker with a kernel mode read-write primitive can corrupt this and make this page metadata say it's executable, and the CPU would gladly execute it. But we're executing in a VM now. So all memory access needs to get converted into a system physical address. What has to happen? The extended page tables are looked up. So all of the execution now on Windows retrieves the extended page tables to actually validate that this is kernel mode, readable, writable, executable, all of that. Because again, these page tables are located in NT. An attacker with an arbitrary read-write primitive can execute them. But this is going to get compared, this PTE, to the extended page table that's managed by the hypervisor. You can't corrupt those page tables from VTL0 because they're managed by the hypervisor. You have to ask the hypervisor to do so. So anytime, let's say this memory is kernel readable, writable, executable, the machine will crash because when the extended page table is fetched, the extended page table will say, whoa, 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 VTL1, because again, VTL1 can configure the extended page tables for VTL0. The hypervisor will go, whoa, VTL0 configured this page to say it was kernel, readable, and valid. But the guest physical address says that it's kernel, read, write, execute. That's a mismatch. Someone must have corrupted the page table entries, crashed the system. Hopefully, that's a long-winded way to say VTL1 is secure world. It's allowed to configure VTL0 as it sees fit. VTL0 is treated as a virtual machine. And because of that, all of the memory accesses, we can think, again, it's simplified, but all of the memory accesses are gated by the hypervisor. And all of these permissions are applied on physical memory because, again, when the extended page tables kick in, we no longer care about virtual memory because we're taking a guest physical address and converting it to a system physical address. So those permissions are applied on physical memory. Now, again, last thing to say on this is I showed earlier the example of, what VM1 thinks is hex or physical address 2000 is really 4000 on the underlying hardware. When VBS is enabled, we actually don't need the extended page tables for the translation. They're just being abused, so to speak, for the access rights. Because as I said, a VTL is just physical address space with an associated access rights. All of the physical memory is actually identity mapped with VBS enabled. So what that means is when VTL0 goes to access physical address 8000, that is really physical address 8000 on the machine. We don't care about the actual translation. We don't gain an additional benefit by, putting VTL0 in its own physical address space and then VTL1 in its very small physical address space. We don't gain anything by that. All we care about is the actual control bits from the PTEs. So when VTL0 goes to access, K user shared data, that's going to be at PFN, the page frame number of 8A70. So if I do view dump physical memory at 0x8A7, and I multiply that by the size of the page, we get the actual physical contents here. So if I do, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 6, 7, 8. See how these memory contents are the same? This is the physical address associated with this. This is the same physical address that VTL1 has access to. But again, we don't care about the translation. We care about the actual control bits. That's all we care. Now, you're probably wondering, why am I bringing any of this up? Why does this matter? So I'll get into that. But first, was there any questions, Steve, about any of this so far?
There's a bunch of questions coming in. I'm trying to field a bunch of them.
Okay, no worries. And again, this is just kind of the setup, so I can. I'm about to articulate why CET is relying on this.
Yep.
So if there are any, feel free to please stop me. But moving on. So everyone has probably heard of kernel control flow guard, or just control flow guard in general. So you have, guard. So you have this, the way that CFG works, as I mentioned earlier, and again, I promise I'm getting to the point here. We mentioned CFG earlier. So CFG is a control flow mitigation that investigates forwards edge calls. So actually, if I do call. Oh yeah, some of this stuff. It's actually here. Okay, great. So CFG is a forwards edge control flow mitigation. What that means is on Windows, you sometimes have something known as an indirect function call. So think about on Windows for a second. You're compiling an application and you're saying it needs to be able to call virtual alloc. Well, the code for virtual alloc is located in kernel base.dll. My program is called program1.exe. So I need some way to be able to call into kernel 32. What happens is a call will happen through a pointer. You have something called an import address table, which has a list of all of the imported functions that need to be called. It's in the metadata of a portable executable. And what happens is you do a call, and it doesn't call virtual alloc directly, it calls a pointer. The reason why that's an indirect function call is because who's to say at compile time that didn't get corrupted? The pointer was corrupted to go to virtual protect or some other thing. Another example of this is calling through a register. So you may have, call RAX. RAX gets computed at runtime. So because of that, there's no guarantees of what's going to be in RAX. This is what attackers abuse in order to invoke their own code. Is they're somehow able to control the contents of RAX, and then natural execution will take them into executing the code, right? So Microsoft has a mitigation against this. What happens is when you compile an application, all of the calls that result, all of the control flow transfers which result in one of those indirect function calls, so a call through a pointer or a register, all of those functions are known as the valid call targets. Those get broken down into bits and are inserted into the control flow guard bitmap. In kernel mode, there's only one bitmap because the kernel mode address space is shared, and it's managed by this symbol. So you have this bitmap. And what happens is anytime one of those calls happens, so we can see it here. Oh, wrong one. If I unassemble this, anytime, so in this case, how dispatch table is an array of functions leveraged by that for how functionality, so to speak. And it's an array. So if I do this, see, this is an array of functions. So when a call happens, an indirect function call would say, call this address through this pointer. So again, call whatever is contained in this address, which would just be how examine MBR. Now what happens is instead of just crawling that directly, we have a call into this kernel control flow guard dispatch function. And what it does, it says, hey, I'm about to call whatever is at HAL dispatch table plus 8, which in this case is HAL query system information. Before I do that, validate with control flow guard that whatever's at HAL dispatch table plus 8, which is this HAL query system information, validate that I knew about that when my application was compiled. So validate that the kernel knew about this when it was compiled by checking that bitmap, because the bitmap contains the metadata that corresponds to all of the known call targets. Again, that process is more convoluted, but that's the gist of it. So think about from an attacker perspective. Microsoft threat models all of their mitigations for the most part. Again, I don't work at Microsoft, just from research that I've done. Threat models all of their mitigations, assuming an attacker has a read-write primitive. So if I am trying to implement kernel control flow guard, I am assuming an attacker has kernel read-write primitive. If an attacker has a kernel read-write primitive, what's stopping them from taking this bitmap What's stopping an attacker from locating the bitmap, using the read-write primitive to corrupt this bitmap, and note every single function as a valid call target, right? So if the attacker is able to allocate some shellcode, what's stopping them then from taking the bitmap, using their read-write primitive, corrupting the bitmap, and marking their shellcode as valid so that when the CFG check occurs, it passes? Because if I allocate some shellcode at a random address, that wasn't known about at compile time, so CFG will fail because we don't want to allow function pointer corruption to occur. That's why I explained earlier all about VTLs and gating memory, because what happens is VTL HVCI is actually, or excuse me, not VTL. This because it's an NT. So put this aside for a second. So HVCI and VBS allow VTL1 to explicitly mark the control flow guard bitmap as read-only at the hypervisor level. So even if an attacker is able to corrupt the page table entry corresponding to the CFG bitmap and say, hey, I know this bitmap is read-only, but I'm going to make it writable. So that way I can corrupt the bitmap and mark everything in the process as a valid call target. VTL1 actually configures that bitmap to be read-only at the hypervisor level. So when you actually go to do the write, yeah, you can gladly corrupt the local page table entries managed by the kernel to say this is a readable and writable page, but it's going to kick off because again, the hypervisor is intercepting this. Again, I don't want to conflate with hypervisor intercepts. I'm just using generic terms here. The hypervisor is able to see that because that address has to be converted from the guest physical page to the system physical page. It gives it a chance to look at the page table entry and it goes, hey, this bitmap is actually writable. I said, ergo VTL1 said that this bitmap should be read-only. And so that allows the hypervisor to protect the kernel control flow guard bitmap. If that did not exist, kernel control flow guard would be useless because, again, the bitmap could be corrupted by an attacker with a kernel read-write primitive. Well, kernel control flow guard is defending against a kernel mode attacker with a kernel mode read-write primitive. So it's kind of a kernel defending against itself situation, right? All of this to say, this is also needed for shadow stacks. Just as the kernel control flow guard bitmap is protected by the extended page table entries, so also all of the shadow stacks, the kernel mode shadow stacks, need to be by VTL1. So the thought process here is that anyone that accesses a kernel mode shadow stack can either be a higher security boundary, which is VTL1, or hardware. And that's why HVCI is required in order for kernel shadow stacks to be enabled. All of this stuff works together. And so it's fairly interesting. So now I'll kind of go through a little bit of the flow of how this looks and showing a little bit of debugging the secure kernel as well. So I'll stop sharing the screen. Again, if there's any questions, Steve, please let me know.
Yeah, no, nothing that I didn't field.
Yep, no worries. Okay, so I will go to NT. My worry is that my IDA is going to be small.
I mean, there is the question that if you were starting your career today, would you focus on binary exploitation still or something else? But that's outside the scope.
Yeah, no, I definitely would. I kind of see myself nowadays just more focusing on the Windows internals because it kind of encompasses everything. You know, I've had questions before asked of me by people who are more doing way more exploitation than I am recently, just kind of little nuances about like kernel control flow guard and stuff like that, you know, another little anecdote I was talking in a Discord server about. So as I mentioned earlier, if HVCI is off, kernel control flow guard is not enabled. It just lets all the stuff go through because what's the point? As I mentioned, the kernel's defending against itself, except for one situation. All of those CFG protected functions, if you override it with a user mode address, there's a bitwise test that's done that says even though kernel control flow guard is disabled, you're calling it to a user mode address, blue screen the machine. So you do get some level, those are just little nuances that you pick up from just looking at the sort of stuff that's not really like widespread documented, so to speak. So having a knowledge of all of that will help you with exploitation So I would just encourage folks to just get involved in Windows internals in general. Write your own driver. Um, Watch like Alex INS has so many talks online. Start with even some of the older ones. Just get involved there because there's so much overlap between the exploitation world and the Windows internals side. They say with software development, X% is actually writing the code. Let's say, it's 10%, 90% is testing and validation, right? I view exploitation as 10% you're writing the exploitation code, 90% you're getting familiar with the target that you're interfacing with. Yeah. And having a knowledge of that really helps. So.
Yeah, for sure. And you just reminded me, now T actually asked a question, why did Microsoft decide to crash the Windows rather than like restoring state or something? I imagine something like the complexity with the TLB and the constant changes, but what are your thoughts?
Well, in kernel mode, it's kind of just, I don't want to say best. I mean, I guess it is best. The reason why a blue screen is happening is not just for the sake of crashing. It's because you can, break your system or do something else. It's the same thing with user mode, right? Like anytime one of those user mode mitigations gets violated, except in a few cases, your process is going to crash. For the most part, it's kind of just the same methodology. Because another example is you're then in the infinite, permutation land, so to speak. Okay, what do you need to restore? Yeah, you can restore the kernel control flow guard bitmap or something like that. But there's an attacker, obviously, that can corrupt them. Where are they located? How do we restore? There's just an infinite number of things. So I'll get into this now, kind of just what the actual implementation looks like. Again, this is mainly probably just me going over my blog a little bit more. And I'm not going to show that much of debugging the secure kernel because I'm using this tool called SourcePoint, which is like a hardware JTAG debugger sort of thing. And it's kind of like in beta, I feel like right now. So it's kind of hard to use a little bit. And it's definitely prone to some demo issues potentially. So I'll just show at the end a little bit of doing that. But what I'm going to go through now is mainly what's in my blog of how we go from the shadow stack being created to the actual corner cases like context restores on threads or from exceptions, stuff like that. But basically what happens is it all starts with thread creation, right? Because again,
that code's really small if you want us to see
it. I'm not sure how to zoom in on IDA, to be honest.
Can you change the font size maybe, or?
Yeah, to font. Oh, here we go. Oh, there we go.
Perfect.
Okay, that's nice. Is this better?
Yep, way better.
Okay, great. So what happens is this is in the allocate thread functionality. So again, thread's being created. The thread has to be initialized, and all of this stuff is like let's go back to this. Like all of this, these are not documented. This, like, I just named this init thread arg, so I just kind of reverse this as best I can. So there's no, like, I don't want people to go in the symbols, oh, there's init thread args. That doesn't exist. Basically what happens is the thread initialization happens and a bunch of this stuff gets set up. What I am specifically showing an example of is how the kernel mode shadow stacks get initialized and created for a user mode threads kernel stack. Again, when we think of a kernel mode mitigation, like kernel shadow stacks, we immediately think to, oh, stacks are associated with threads. This is a kernel mode mitigation, therefore this is associated with a kernel mode thread. Again, for those who are not familiar, when you issue a system call on Windows in most cases, the actual thread from user mode, like if a user mode caller issues that, when the actual system call occurs and transition goes into kernel mode, it's still on the user mode thread. But there's a context switch that happens where you're on that thread's kernel mode stack in kernel mode thread state. So the user mode thread is still going to have a kernel mode shadow stack, if that makes sense, because of those scenarios. So the whole blog that I did and whatnot is about specifically user mode threads, kernel mode shadow stack. It's pretty similar with a lot of the other stuff, but you just have to pick one because there's nuances with everything, right? There's weird situations for like DPC stacks and ISR stacks, interrupt service routines, like things that I did not investigate. So I just want to make that clear. So you kind of gather all this information because this is going to be user mode thread. This is the underlying NT address, which is going to be called to actually start the thread up itself. And a bunch of this other information is provided, right? So the stack itself is one of the first thing that's created, not the shadow stack, but the actual stack itself. And then we come to the first check. What the first check here is it says, is kernel CET enabled? I'm going to go ahead and show this right now. The way that this gets set is if the CR4 register contains this bit set, it gets enabled. And what this is if you read the Intel documentation, CR4, I forget exactly which bit this is. It's like 50 something maybe. I really don't remember, and I don't want anyone to quote me on it. But if this is set, it gets enabled. But again, what did I mention earlier? I said earlier that we need HVCI to be enabled before we can enable kernel CET. This is just looking at CR4. So I was kind of bewildered at this at first as well. What actually happens is the way that this here, I'm actually going to probably need to stop sharing this one because I have another IDA screen I need to share. Font, larger. If there's questions, please let me know as well. Present, share screen.
Just some comments
just feel free to interrupt me too. Like, it doesn't bother me.
Yeah, I was saying just some comments around like Microsoft moving to Rust, and are they going to keep focusing on mitigations or just focus on more of a secure programming initiative? Then there's all that legacy code and compatibility issues of all decades and decades of use. It's challenging.
Yeah, exactly. So who knows what's going to happen? I mean, we can obviously see there's a move to Rust. Just look at the Rust crates. I don't think it's prime time for some of the Rust stuff yet. You know, but again, that's probably another conversation, especially in kernel mode.
Yeah.
Oh, but this is winload.exe. And in order for CET to be enabled, there's this function called get effective kernel shadow stacks configuration. There is a registry key called kernel shadow stacks. I have a blog about kernel control flow guard and HVCI. It's called No Code Execution, No Problem, I think, on my blog. And it talks about kind of, you know, the future of CET and whatnot. And at the time, there was no toggle that you can do for kernel CET. There was a registry key that Yarden helped me identify. And when I say that, I mean she literally identified it and told me. Called in the device guard registry tree, something called kernel shadow stacks, which can have an enabled key and also audit mode enabled. Audit mode will allow you to, like when a CET violation is incurred, you don't blue screen the machine, you just log it to ETW actually, which is pretty interesting. So this function gets called in this OSL set VSM virtual secure mode policy. And you see, you can only reach the shadow stack policy because the registry is one of the earlier things that comes online. Even though we're in WinLoad here, this is all queried through the registry. Before we can even get to check the shadow stack policy, the first thing that's done is it checks if this is HVCI enabled flag present or Boolean present. And the way that this gets set is through this get effective HVCI configuration, which will call this get dword value on enabled for hypervisor enforced code integrity. So again, we only start processing the kernel shadow stacks policy in win load, which is even like really early in the loading process, if HVCI is enabled. So that's exactly how that gets set. So you have to have HVCI enabled. So now I'm going to go back to NT window and kernel share xref. So I believe this gets gated. No, it wasn't. Okay. Anyways, so to even get here, it has to be enabled on the processor, and HVCI has to be enabled. And what happens is each thread needs a special type of handling. Well, I shouldn't say each thread needs a special type of handling, but we delineate what kind of thread is there. I call this shadow stack type, right? So the thread has something called MISC flags. I can stop sharing this and go back to the debugger to show a little bit about that.
If someone's asking, do you think being able to read, write, analyze, assembly, and decompiled code will still be useful in the next 5 to 10 years? I say yay.
Yes, absolutely. I've had conversations with folks too. It's interesting because if you look at least in my anecdotal opinion, a lot of what we see now, people are very interested in, command and control framework, C2, offensive tradecraft. Who are going to be the people left behind that are interested in systems programming? I'm not talking systems programming like from an exploitation perspective, but interested in systems programming for like operating systems and stuff like that. Yes, there's obviously a lot of people that are involved in that community, but who are going to be the people left behind that do that? You're going to get crash dumps that you have to triage, that you have to investigate, root cause analysis. Why did this crash happen? All of that is going to involve reading assembly code. When you're triaging it. So if I look at NT K thread MISC flags, and luckily they're all in the symbols here. So offset 74 is everything above. So up to here. These are all the flags which can be set. So we can see a flag called CET kernel shadow stack. This means this thread has an associated, CET kernel shadow stack, user shadow stack. This is a system thread or a secure thread, which is very interesting. I mentioned in my blog, these other various flags that are not of interest to us. APC queuable is something that's frequent. So let me stop sharing this and go back to screen for NT.
Nop says, a very important question, Connor. When are you finally going to attend Offensive Con?
Oh, goodness. Yeah, I know. I actually, I'm embarrassed to say, I just got a passport like not that long ago, and I've only been out of the US once. So I just need to brave up and do it. I'm just a homebody. But I'll definitely come say hi to you, Nop, at Offensive Con. So you have these MISC flags, right? And based on what some of these flags are, and you also have these, what I'm just, again, init thread args is not documented, flag is not documented. But if MISC flags contain 0x4000, if you actually break down what this is at a binary mask, it corresponds to that system thread. But then you also have this other one, this else statement. And this actually, if this MISC flags is parsed, when this gets parsed, it actually corresponds to the secure thread bit. So when this bitwise shift 8 and bitwise and with 1 occurs, if the result is 1, secure thread was sent. If it wasn't, I'm just calling it a user or a normal. Again, this is not documented. This is just from my reverse engineering how this looks, right? So, and then this gets forwarded onto this KI created kernel shadow stack. This is going to do all of the stuff which I'll mention in a second. And if this is successful, the thread object, the K thread object itself, manages the kernel shadow stack, shadow stack initial, base, and then all fields, which are just some of these fields put together. A lot of bitwise operations. But yes, that's the gist of it, right? So, and then when the cleanup happens, this shadow stack, if it was created, if it failed, it'll go and delete it. So this is kind of where the quote unquote magic happens, right? So ki create kernel shadow stack will call into create kernel stack. And this is a generic function if I view xrefs. Oh, you actually probably can't see this, xrefs. Oh, that is unfortunate. But it's used in a bunch of function calls. So ke init thread, ke allocate calls stack x, ki create kernel stack, ke user mode callback, allocate processor stacks, allocate x state stack, ki expand kernel stack, and call out. So it's used in a bunch of different scenarios. It's like a generic function. And this is why this structure, which again is not documented, I'm just calling it nm kernel stack context, has a lot of these generic parameters to say, what's the stack type? What are the flags? That sort of thing, because then you can call this generic. And so this gets called. So let's go through some of this stuff. So this is not, I don't want to spend time on all of this. Let's see where I want to go. Okay, well, I won't do everything here. I'll actually show you a few things. So this is the K-less one. Where's the PRCB? Give me 1 second to find this. Okay, current PRC. Okay, great. So there is a code path which can be taken that uses a cache shadow stack. So the PRCB, which is like a big structure that denotes information about the current process, each processor is associated, each logical processor is associated with one, I believe. Don't quote me on that. And it gets the current, so the current processor, which is servicing this call. There is a special field. Oh, it's using it's trying to parse. So this is actually, I think my types may have been messed up. This is actually wrong. So let me stop sharing my screen and go back to the debugger so I can show that. Reset, share screen, debugger. So okay, so this is actually what it should be pointing to. There's something called cache stacks. Historically, as of like Windows 10 1703, there was only one. It was called cache stack. Now you can infer there's two. One for the shadow stacks and one for the regular stacks. And I won't get into like, because to be quite frank with you, I didn't spend the time to reverse engineer how those actually get set. I can show you in the code. I don't know exactly why or like under what scenarios they do get cached. So let me come back to sharing this now. So if you look at NTOS, so this actually should be that cached stacks thing. And what happens is we go and we look if oh, was it because yeah, okay.
Sorry, cut out there a little bit.
Yeah, no, all good. I think I was just stopping talking anyway. So this PRCB, this cashback index, depending on whether it is a user or a regular stack or a kernel mode stack, what happens is if one is present in the PRCB that can be used, it's a singly linked list. and it's popped off the stack. And what happens is this validate kernel shadow stack gets called, and it just does this sort of check right here to validate the reference count effectively. So that's one way you can get a cached stack after a kernel shadow stack is used, because it has to incur the cost of doing a secure system call, which I'll show in a little bit, to call out to the hypervisor to set the permissions and everything. It's like a performance game that every time you want a shadow stack, you don't have to call out to the hypervisor every time. If we can cache one, there's actually a function called like is ideal for caching. If we can cache one, then that's what we should do instead. But there's also another one. Where is this? I think it was up a little further. Sorry, you guys are seeing the text really well. It's massive on my machine, so it's kind of like hard to read this. So on Windows, there's this notion of partitions now. I won't get into all that. You should read the Windows internals book about it. But we can think of, on my machine that I'm doing, there's only one partition, and it's just the standard. Don't conflate this with like root partition from Hyper-V perspective. This is just a memory partition, and there's only one. It's just all of the address space, so to speak. Again, Windows internals people will crucify me for saying this is just simplified, very simplified. So what happens is each partition, each node, which is like a grouping of processors, has a list of cache kernel stacks as well. And the parsing in IDA wasn't liking this, but really that's what this is. So that's one of the things that's retrieved. And there's like an array of 8, I believe. And so what happens is the proper index is fetched, and it checks if that cache is empty. And again, this is another singly linked list. And if there's a stack that's present, we can use it. It'll pop one off the stack, the singly linked list, and it will call this update kernel shadow stack owner data, fetching the associated PTE and whatnot. And so, you can see here, beautiful. So what it does is it looks at the free shadow stack cache entries, and it pops one off. And again, the parsing here is off because this is a large function. I didn't fully reverse the whole thing. And it will update the information about it from the cache. So that's one path that can be taken. And it validates that it's a shadow stack page. Right, this is all done in NT. But that's not the interesting part for us. So there's a caching process that can be used. I talk about it more in the blog, but it's not of interest to us because it's just reusing something that's available. And it would be particularly interesting to see what the security of that is. I didn't have a chance to look into it, but so vulnerability researchers out there, can you do anything with that? I don't know. Could be interesting. But you have this allocate kernel stack pages, and this is kind of the larger, so to speak. Oh, I didn't show that. Or was it in the allocation routine? Because I want to show how the memory is grabbed. Yeah, it's not here. It's up here. So pointer PTEs. Here we go. So we can see this right here. PTEs. Let's see where it actually gets allocated. Reserve PTEs. This is what we want. So what happens here is, depending on the stack type, this reserve PTEs is going to reserve the actual page table entries for the shadow stack region that we care about. And depending on the type, it will go to 2 different places to get that. So let me show you what that is in my debugger. I know I'm not showing it right now. This or core. Um, my point being here is that there are two places where you can get stack PTEs from. You can get it from the region of memory dedicated to shadow stacks, or you can get it from the region of memory dedicated to regular stacks. So I'm actually just going to share it from my blog because I have the screenshot already pulled up. So let me share this. And again, if this is boring to everyone, I'm sorry. It's interesting once we get to the secure kernel stuff.
It's good to see the, hey, I got to find out where I am. And oh, that's where
Yeah.
that is. That's how the puzzle works.
Yep. Oh, I don't want to share the screen. I'm sorry. Stop sharing. I want to share. I want to share this. You should be able to see the blog, hopefully.
Yep. Looks
okay.
Good.
So MI state is where this comes from. This is actually a better place for it. So MI state contains a lot of the known regions of memory, especially for PTEs. So as an example, it contains the regions where you can reserve PTEs for system memory functions. And there's one called kernel stack PTE info, and there's two indexes. There's index 0, which is right here, and index 1, which is right here. If you look at the actual VA type, there's an enum of system VA type. There's one called MIVA kernel shadow stacks. So when the kernel shadow stack routine is going to reserve PTEs for the actual pages for the kernel shadow stacks, it actually does it through NT, through this right here. So coming back to window.
Never had so many screen context switching.
Yeah. I know. I'm too nervous to just share one screen and then my wife messages me or something hey, I need this or that. I'm like, I'm trying to do something. So then the reserved PTEs. This is simple. The number that are needed depending on the type of stack that's computed this way. And then 5 is actually what denotes the beginning of the shadow stacks from my research. The stack type that's actually passed in for user mode is 5, I believe. 5. Yeah, 5. So it will reserve the PTEs. And then all of this gets used to allocate kernel stack pages. This is what the interesting part is. Because for shadow stacks, we eventually come down to here. VSL allocate kernel shadow stack. So again, we've gone from thread initialization, figuring out what kind of stack is going to be used, reserving the page table entries, and now we're at the point where we want to configure the shadow stack. But again, HVCI is required. So actually, this is going to be the secure kernel which does this. So if the processor supports shadow stacks, and I kind of hinted to it earlier, but this processor supports shadow stacks, this MI flags actually gets set by that winload.exe checking the policy for if kernel shadow stacks are enabled, which is reliant on if HVCI is enabled. So what happens is the target shadow stack base address from PTE, this is just the PTEs that we reserved being converted into the actual virtual address that we care about. The number of PTEs is changed to this. Anytime in memory operations you see this operation, you can infer you're either going from number of bytes to number of pages or number of pages to number of bytes. This translates to C in hexadecimal. That's just a common compiler optimization, I guess you could say, for when you want to convert. So the number of PTEs, it expands it out to change it into the actual number of bytes. The stack type, the page frame numbers. So the actual physical page frame numbers associated with this virtual address, the base of the shadow stack region we want to allocate, the number of PFNs, and then this contains the output shadow stack. What this actually does is it invokes VSL enter IUM secure mode. This is a wrapper to emit a secure system call. Secure system call is going to be a hypercall, effectively, which reaches out to the hypervisor to transfer execution to the secure kernel. And so just like how a normal system call has a dispatch number, so right, like every red teamer has seen this, oh, we want to do direct system calls. We don't want to call the Windows API, so we load, 59 into EAX, and then we invoke the syscall, and we can achieve the same thing. Same thing here, same kind of concept. You have a secure system call number and then actual packed arguments in the structure. The argument structure is going to change for everything. We'll see that when we go to the secure kernel debugging side. So the arguments are going to change. This is not documented. This is just my reverse engineering of this. So you have the base region, that's just from the PTEs we reserved of the virtual address. And again, the PTEs themselves are not necessarily mapped in at this point because we want to ask the secure kernel to set everything up first before we do anything. So get that. The array, so we take the actual page frame numbers. 8 is the size of a pointer to a PFN times the number. In my testing, this was always 1, just 1. And stack type. So this is going to enter VSL, enter IUM secure mode. I'm not going to go into this more because this is going to set up the actual switch to VSM VTL1. And then if this is successful, so greater than 0 is if you've ever seen the NT success macro before, what that does is you wrap results from an NT status in that, and it checks if it's a failure code. The way that it does that is a negative value. So this says, is it 0, which is status success, or higher, which is also a success value. And it reuses the field for number of bytes for the output of the shadow stack. This is most likely because this is probably actually a generic structure. It's just not in the symbols. So anyways, so now, again, started at thread initialization. We've gone to figuring out all this stuff. Are we hitting the stack cache path? Reserving the page table entries. Is CET support enabled? Going through the actual allocation routine. And wound up at the secure kernel. So I'm going to stop sharing this screen, and we're going to go to the secure kernel screen. Let me change the font. 6 slide.
So you might be covering this later, but someone's asking if it's the call instruction that is actually what triggers the pushing of the return pointer on to the shadow stack.
Yeah, so please, no one quote me on this. I'm almost positive that it has to do with the microcode of call that implicitly it also causes the shadow stack to be pushed onto the the return address onto the shadow stack. But again, I just haven't looked. But I want to say that I heard that. But again, I'm a very, very, very fallible person. So share screen, window, secure kernel. All right. So the secure kernel has this function called IUM invoke secure service. You can see this local allocation failed because this literally handles every single secure system call for the most part. And the ID of the shadow stack one is 230. And so I'm not going to reverse engineer this entire function, but I did do the handler for the secure system call for allocating kernel mode shadow stack. So execution will pick up here in this function. So if the secure system call value is 230, we hit this code path. The first thing that happens is this translate kernel shadow stack type. This is probably just some internal wrapper. In fact, it is. If you just look at it, if the shadow stack type is this, set this value. The reason why this is done is there's just the secure kernel probably is just isolating its constants and stuff from NT so they don't share the same stuff. But it's also, depending on what the shadow stack type is, this flags is actually very important. There's something called the shadow stack token, which we'll talk about in a little bit. And depending on what kind of shadow stack is being requested, certain flags get set, and those flags denote what kind of token should be used. So translate it happen, get the flags and type, and then this create NT kernel shadow stack. You can see 231 likely refers to cleaning up shadow stacks. We'll get into NARs a little bit. So this is the meat of everything right here, this function. So first thing that happens is a bunch of these checks occur. This refers to, this might refer to HVCI. I haven't fully reverse engineered this. It looks at the shadow stack type, number of bytes, number of PFNs, that sort of thing. So in this case, like I said earlier, normally the number of PFNs that was provided is 1. So if the number of PFNs is 1, and we do this bitwise shift by 12, again, I said talk about number of pages to bytes, bytes to pages. This is going to change 1 to 1,000, which is the number of bytes in a page. So if number of PFNs was 2, this bitwise operation would do 2,000, right? And the number of bytes total is 3,000. So the first thing that is done is something that's called SKMI reserve NAR. This is only really talked about in the Windows Internals Part 2 book by my friend Andrea, who documented a lot of this, who also helped, I have to say, I asked Andrea some questions about this, and he helped me. I was like, why am I seeing this behavior in a few cases? And he was gracious enough to help me. Same with Alex Ionescu and Yarda and Shafir as well. So definitely thank you to them. So SKMI reserve NAR, it's talked about in that book, but NAR refers to normal address range. A normal address range in context of the secure kernel is effectively this structure which says, hey, the address associated with this NAR or normal address range, we now care about at the secure kernel level. So anytime a driver loads, we care about that driver because we need to, when the image is being loaded, we need to parse the sections of that driver to make sure they have the appropriate permissions set, make sure they're aligned properly, all of that kind of stuff. Because if we're going to load and we have HVCI VBS enabled, we want to do validation to make sure you're not just arbitrarily loading random stuff. The way that's done is there's a NAR which says, hey, VTL1 secure kernel now cares about this address range. So a NAR is reserved for the address space associated with the shadow stack. And the NAR is a normal address range, or you could call it an NT address range. So it's the actual NT address of the shadow stack, and now secure kernel is aware of it. You can ignore all of the calls to this SKMI get PTE trace. This is one of the main things I had to ask Andrea. I'm just like, this code never executes. Like every time it executes, it just says, it just doesn't even go through here. This is actually debugging for debugging purposes for page transitions. So anytime a PFN is updated or something called an NTE is a normal table entry, which describes a given page that we care about. So NAR is the region of memory, NTE is at a page level that we care about in NTOS kernel. And NTE works very similar to PTE in the sense of there's a linear address which contains an array of all of the known NTEs. Same exact thing. If you ever look at MI get PTE address, how you go from a virtual address to its actual PTE, take the address, it does a bitwise shift, and it aligns it. What this actually does is it fetches something called the virtual page number. Just like each physical address has a page frame number, each virtual address has a little less known cousin called a virtual page number. And then that virtual page number is the index into that array, and that's how you find the associated PTE. Same thing with NTEs. None of this really gets executed because in release builds, we don't care about these state transitions, so to speak. Sorry, I dropped my pen. So you can ignore all these SKMI get PTE trace. So once the NAR has been processed, the next thing that happens is for all of the page table entries that are associated with the kernel shadow stack. So again, in our case, it's just one PFN associated with the shadow stack. For all of the PFNs, this claim physical page happens. What that effectively does is it says, secure kernel is now going to operate on this physical page. So it takes this says pointer PTE as PFN array. What that means, again, this original virtual address, we did MI reserve PTEs, which outputs a pointer PTE, which is a virtual address that's associated with the page table entries for that region. That can get converted into the actual virtual address of the region itself. So what happens here is the pointer PTE as PFN array. So it takes that pointer PTE from the reserve. So the page table entries reserved from the call to MI reserve PTEs, but as a physical address, it claims them. Okay, so it says, hey, secure kernel is about to operate on these. Then something called the hyperspace PTE is created. A hyperspace is I don't fully understand it, to be quite honest with you. It's documented in Windows internals. Hyperspace is like this temporary place where you can map in memory fairly quickly, but it's not associated with the working set of a given process, is how I understand it. So, like, whenever page table entries are invalidated, as an example, that's done in hyperspace. That's kind of the extent that I know about it. It's a place where you, in our purposes, you can temporarily map something into virtual memory to operate on it. So what actually happens here is the physical address. So again, VTL1 does not set permissions on virtual memory. It sets it on physical memory. That's very important, physical memory. So we have the physical memory associated with the target shadow stack region. So what it does is it creates a hyperspace PTE. So hyperspace in the secure kernel. That allows the secure kernel to map in the shadow stack region into the secure kernel's virtual address space. So it's not mapped in NT space, it's mapped in secure kernel's virtual address space. The way that that's done is it allocates a hyperspace PTE, and then it constructs a page table entry. So it takes the PTE. So again, if you know anything about page table entries, it's comprised of a set of control bits plus the actual PFN. The PFN is the page frame number. If you take the page frame number and you multiply it by the size of a page, that's the physical address of the PTE, essentially. So you have, or of the physical memory that the PTE represents. So what this does is it constructs a page table entry. These are control bits. I know this like just from my exploitation experience. When I see 63 and 8, I'm almost positive this is valid with readable and writable permissions. Constructs that with the PFN. The PFN will be located just before this in these bits. That's why this mask happens. So whatever this is, it'll get put here. And it puts that in the hyperspace PTE. The contents of the PTE are associated again with that hyperspace. And SKE 0 pages is called. This zeroes out the shadow stack region. So it's completely zeroed out. The reason we have to do this, CPUs operate on virtual addresses still. So all these instructions don't operate on physical memory, they operate on virtual memory. So that's why we map the shadow stack into the secure kernel. It zeroes out the memory, and then it calls initialize NT kernel shadow stack. Okay. So this hyperspace PTE, it parses this. What this actually does is it fetches the virtual address of that the page table entry represents. So for all intents and purposes, this second parameter is literally the shadow stack virtual address in secure kernel's address space. Yep,
That's
go ahead.
cool. I had no idea that hyperspace was used for the shadow stack stuff, but it makes sense and it's dynamic on 64 bits. So that's cool.
Yeah. Um, and so now we can see that the flags are coming into play. So what initialize shadow stack does is, oh, also please ignore these comments. They may not be right because as I was doing the blog, I was figuring stuff out. So what this does is it initializes the kernel shadow stack. And how this looks is there's two things on the kernel shadow stack. There's the first return address, so to speak, but there's also something called the token. The token is how the validation is done. All the token is it's placed at the top of the shadow stack, and it is just the address of the token with a lower bit that can be toggled. That lower bit denotes if this is an in-use or a not in-use shadow stack. In our case, go ahead, Steve.
I was hey, good. Glad you caught that. Ende is asking, does cache validation happen in this context as well, like what a translation look-aside buffer is, or have there been any exploits where cache was corrupted?
Like what I talked about earlier with the caching of the shadow stacks, I'm guessing.
Yeah.
So that's actually something that I have not looked into. So the best way that I can explain it is there's not going to be any cache stacks available when you first come online. There technically could be, but there's not going to be any that have not gone through the full path one time, if that makes sense. So all of the cache stacks should have at least one time gone through this process. And as I'll get into, the last thing that's going to be done is set read-only permissions, just like the kernel control flow guard bitmap at the extended page table entry level. So it's going to be read-only in context of VTL0, and you cannot corrupt it, just like the CFG bitmap. So if there are things that are done with the caching, it still looks like it is done in NT, like fetching it and updating the shadow stack owner information. But all of those cache stacks had to have gone through the full path one time. That's as far as I've gotten. I think it could be interesting to look at from a vulnerability research perspective. Is there anything you can do with those cache stacks? I don't even know the particular reasons why, like in one case you go through MI state, another case you go through the kernel processor region control block. I don't know why you go through those two. Again, that probably could be a blog in itself, just the caching path for some of the stuff. It's fairly dense, at least for a guy like me. So what happens is that the bottom of the shadow stack is fetch. So you have this token. The token is literally just the address. So you can see the actual shadow stack based linear address. So it's just the address of the bottom of the stack with a 1 on the end of it or not, to denote busy or not. But you also have something called a restore token. A restore token is used for a shadow stack that is not currently in use. But when a context switch happens, the processor, when it goes to load in the stack, because again, a context switch happens, the CPU register state is going to change because the thread execution is going to change. So that's going to change the stack. But again, now we have CET. So there's also the shadow stack you have to consider. So the shadow stack preserves through this token because the shadow stack can be accessed through the module-specific register, the MSR. So there's a special MSR for shadow stacks. And again, it's protected. Like I'll show why it's not the same as like just corrupting. You can't do that. Even with secure kernel patch guard, which catches a lot of that stuff, because it's at the. Anyways, I'll show why. But this restore token is used for, so when the context switch happens, the processor knows which shadow stack to load in for the context switch. That's actually what happens here. In my testing, always user mode shadow stack, user mode threads with the kernel mode shadow stack never had the actual token itself set because it used a restore token. The reason why I use a restore token is because when the secure system call returns, that thread is not immediately going to start execution because we're creating the shadow stack only in the initialization of the thread itself. So when that thread actually goes to execute and the context swap happens, it'll load the restore token in to load the appropriate shadow stack, which is already configured here. And we can actually see that here. There's this target initialization address. from this skmmnt function table. What this actually is, it's an array of function pointers. And it's on my blog. I forget. skmmnt function table. So I'm going to stop sharing this screen for a second just so I can show it on here. Sorry for all the context switching. Pun fully intended since we've been talking about it. Okay. Hopefully you can see the blog.
Yep.
Okay. That skmmnt function table, what it actually is an array of function pointers with the appropriate initialization routine. So there's like ki start system thread. Well, this is a user mode thread. So the first return address, so like the token would go here, FFF8. That's the top of, well, some people will say bottom because stacks grow towards the lower addresses, but you get my point. Of the shadow stack right here. That's where the token will go. Not the restore token from my testing, just the actual token if it was actually going to be used. I did not see that scenario, but again, I only tested user mode threads on kernel mode addresses, for kernel mode stacks. So when the context swap happens and we return back into VTL0, we can go back to starting the user thread because the context swap has happened. So let me go back to secure kernel. Windows, secure kernel. So we're here. So we set up the token. We set up the token. And if it's a restore token scenario, we actually don't put it yet because it gets configured at the bottom here. So if it's a restore token, the regular token is set to 0. Then we determine which initialization address we need. Then we configure the stack token. So flags, bitwise and 2. 2 is the translated flag for user mode threads with kernel mode stacks, as far as I can tell. And what happens is the restore token is just the address of the restore token is the address on the shadow stack where the address on the shadow stack where the restore token is stored, and then the shadow stack is returned. So that's how it's initialized. You initialize the token and the first return address. And then here comes the part which I mentioned earlier. The hyperspace PTE is released because, again, we needed to, in order to be able to write to the shadow stack, we had to write the token and write the return address. Processors operate on virtual memory, so we had to map the shadow stack into secure kernel first to configure it. Well, we no longer need it anymore, so we can release it. But that doesn't free the shadow stack because the contents are still committed to physical memory. It's just the virtual address, which is no longer valid. Then we have this call to protect single page. Protect single page is a call which will actually do a hypercall. What this hypercall will do is it will configure the extended page table entries control bins. So what this will actually do in this case, this 3 argument all this is undocumented. Hyper-V has no symbols. So it will kick off a hypercall, which will say, hey, this physical page, this get physical address, we want to set as a supervisor page permissions with a read only. I'll show what that looks like in a little bit. So protect single page does what this does for all intents and purposes is it marks the physical memory associated with the shadow stack as read only in context of VTL0. I'll show you exactly how that works. I think it took this. Yeah. Okay. So I'm going to show it from my blog because I have the screenshot there. GPA. Target PTL. Sorry, I'm on the other screen. Okay,
No worries.
here we go. Stop screen. So as I mentioned earlier, we're operating on physical memory. So what this does is it's going to set the extended page table entry on the physical memory for this address in context of VTL 0. So let me share this. Come back to the blog. Here's a screenshot. Can you see this okay?
Yep.
So forget this call stack, because the claim physical page under the hood will also map it in as read-only while it's operating on it. So here's how that hypercall actually looks. The first argument is target partition. -1 actually denotes the current partition, which is self, and then the target VTL. So we can think of this again. That's why I stressed earlier, all of that, how every VM is associated with its own set of extended page tables. Each VTL is associated with its own set of extended page tables. So this targets VTL 0. So we can think that this as, hey, set the extended page table entry associated with this VM is how it would be like in a normal environment. In this case, it's a VTL, which is our VM. And then the target mask. So what I showed in this example is for this call, the hypercall code is C, which is 12. And the flags that are set are 11. I actually found this. It's not documented, so I'm just calling it GPA kernel shadow stack, because there is an associated bit in the extended. So I should also say this. The extended page table entry is not the same thing as a PTE in terms of the actual control bits. Some of them are the same, like writable, executable, and whatnot, but there's a ton more bits that are available. One of those is the supervisor shadow stack bit. So it sets that, and it also sets readable. So this is read-only. This memory, this physical memory, when you're operating on it in context of VTL 0, is read-only. Okay, let me come back here, present your screen. Secure kernel. Okay, so initialize. It sets the page permission, and then it flushes everything out, unpins the nar, and returns. So that's literally what happens at this level, right? We have and that's the gist of it. Because as a part of this initialize shadow stack, you see the output comes from the output parameter here. So as soon as the initialization is done, that's the address which is going to go out to VTL 0 when it returns and stored in the thread object itself. So that's the gist of how the kernel mode shadow stacks in this specific scenario is configured. I do want to show now, and I'll try to go fairly quickly, the nuance with it effectively. So assist. All right, so you have this assist functionality, right? So on Windows, the best way you can explain it is there's exceptions can happen, right? So what happens is an exception is encountered. Well, that means the processor, the thread, all that has to stop doing what it's doing right now and go and call all of the exception handlers, right, to determine, hey, can anyone fulfill this exception? And then if that exception can be fulfilled, execution goes back to doing what it was doing before. Well, there's an implicit problem with that. And that is when you go to handle the exception, when you go to call the exception handlers, all of the state of the thread and processor change because you're no longer servicing what you were doing earlier. You're going to mess with the exception. So how do you revert back to what you were doing before? Well, something happens where you construct a let me stop sharing this. Share screen. Intel's kernel. So something happens. We want restore context is probably the best one. So what happens is, if you've ever seen the context structure before, this is, red teamers have used this when they call set thread context. That's an example. Like, oh, we can directly set the instruction pointer on a given thread and resume execution. And because the instruction pointer is the next instruction to be executed, boom, we've executed our shell code. That's not there for red teamers to use. That functionality is there for exception handling and resuming execution after something has happened. In this case, legitimately, after a exception happens, we need to restore execution. Well, how that happens is we use the unwind data to determine, hey, what's the state of the CPU we need to go back to now that we've handled the exception. That's done through a context structure. Well, guess what? The context structure is a very large structure with a bunch of CPU registers. So if I can hijack part of the restore functionality, if I can hijack the stack pointer, the RSP field, and load my own arbitrary value in there, I can effectively get around CET because I can control the shadow stack value. So what happens is we actually have to ask VTL1 to help us every time an exception happens. So this AE restore shadow stack context, this is part of the restore context functionality, which is called on exceptions. And what happens is there's this context EX structure, which Jordan and Alex talk about in their blog on their Windows internals, the RIP ROP. It's this new type of structure. Well, they didn't mention it in theirs, but there's a new substructure called kernel CET context. The reason why we have context EX now is because the first, hundreds of bytes are just a normal context structure because Microsoft made it publicly available. They can't just change the structure format now because so many tools, et cetera, rely on it. So what they do is they create another structure and make the first few bytes the context structure. So it doesn't break existing functionality, but we can pin on to the end additional functionality. So kernel CET context. So what happens, the end of the context structure, the offset to the kernel CET context structure gets added. There's a new flag that you can specify, context kernel CET, which is just the AMD 64 registers with this new bit. And what happens is we call into VSL shadow stack assist. And we have validation on the instruction pointer as well. And so the secure kernel, it's its responsibility to get us back to the to load the appropriate shadow stack. So what I mentioned earlier is the shadow stack is actually stored in an MSR register. It's called IA32_PL0_SSP. That's the ring zeros shadow stack. Then you have PL1, PL2, Windows doesn't use those, and then you have PL3, which is the user mode one. The shadow stack for VTL0 does not get stored in IA32PL0SSP because it is a VM. A VM has an associated structure called a virtual machine control structure. The virtual machine control structure has those MSRs configured for the guest itself. So we can think of the guest the guest is represented, its registers, all that through the VMCS. So what this actually does is it takes the VMCS of VTL0 and it sets the appropriate MSR. So the way that this works is for restoring context, we have the shadow stack and the RIP. The instruction pointer gets validated. Won't get into that. Then this dispatch happens. There's two. There's a validation and there's an operation. I'm going to click on the operation. So you can see this right here. What happens is the target shadow stack is loaded into this register. Oh, I'm on NT. I'm so sorry. Present, share screen, secure kernel. So let me actually go back. So this is the this gets called as a secure system call to say, hey, VTL1, we need to restore the shadow stack because an exception happened. We need the old shadow stack pointer value back. What happens is this assist functionality comes in. We determine what was the reason. Our case, it's restore context. In this case, there's a dispatch functionality which queues up. I can't remember if it queues up a thread or what it does. I forget how actually. You have to look more into this generic IPI, and if that's taking a long time. Yeah, I won't get into that just because I don't know off the top of my head. And you see at the end here, this SHVL set VP register call. What this does is it is capable of setting on the VMCS structure associated with VTL0, one of those MSRs or registers. We can think of that, I don't want to call them MSRs, just register states. There is a register state called the guest underscore SSP. What that says is it's the shadow stack pointer associated with the guest. That makes sense. This is the shadow stack we need to associate with VTL0. And it takes this HV underscore register underscore value, I think it is. And then you also have this value here, which is the HV underscore register underscore name. This is undocumented right now. I actually had to, because I'm very bad at using IDA, what I should say about this. So it takes the target shadow stack we want to restore, and it asks the hypervisor through a hypercall to set that guest SSP with the target shadow stack we want to restore to. It does a hypercall. So this will kick off execution to HV, to Hyper-V. And I actually, because I'm very bad at IDA and like searching and stuff like that, since HV has no symbols, I spent hours reverse engineering where this value is used in Hyper-V. And it's not very obvious to me because like some of it's computed at runtime. So like I was reversing a lot on that and I eventually found it. And so if I stop sharing this now, StreamYard guest SSP, VMX guest SSP. That's what it does. So here I show the register value that's being done. I found this in Hyper-V. So I was using SourcePoint to debug this. I'll show just, I didn't get to it as much as I want just because I was yapping so much. I'll show just a little bit of debugging with SourcePoint just for the fun of it. But I finally found where this register was used with a VM write operation. So VM write is an operation which updates the VMCS of a given virtual machine, in this case, VTL0. The VMX guest SSP register, like the MSR value, is hex 6828. So I eventually found this. And so you can see here, VM write with SourcePoint. The guest SSP, which is the shadow stack pointer associated with VTL0, was this. This is after the restore functionality. And after the VM write, we can see that it was updated in the green right here. So that's the gist of shadow stack in general. The main things I wanted to show was it requires VTL1. So if HVCI is not enabled, you're not going to have kernel mode shadow stacks. There's still some functionality in kernel mode. There's caching functionality. And there is situations where VTL1 has to be relied on in order to restore and help out in some scenarios like DPCs and some other ones as well. So you have to rely on them as well. And those, like the VMX guest SSP is not an MSR that you can just write to from VTL0 because it's, again, managed by the hypervisor. So I'm going to attempt to, if we have time, I was going to spend maybe 10, 15 minutes just showing SourcePoint. If we have questions while I'm getting it configured, please feel free to shout them out.
Yeah, sure.
But I will get this sorted. Put this over here. And it's going to sound like a plane is taking off in here probably. Source point is getting ready. All right, I'm going to open up source point now, and I'll show you.
Okay. Someone wants to know how long you've been working in this space.
I think probably 2020 is when I really started taking it more seriously, I would say. I was really into red team for a while. I was even still doing red team in 2020. Really, when I got more interested in this is when I started working in CrowdStrike, like working on EDR features, because a lot of that is systems programming and whatnot. Look at the job listings and see for yourself online what skills are required. That opened up my eyes a lot. So I'd say in the last like 3 years or so, like that browser exploit online that you were mentioning earlier about like Chakra and all of that, when I really started taking Windows internals more seriously and whatnot was probably more like 3-4 years ago. But 2020 is when I started like wanting to be more technical, I guess you could say. But yeah. Okay, source point.
What would you recommend for folks who want to get into kernel debugging besides just like reading Windows internals and stuff and just diving in and doing it? Any like places where you would tell them to get started?
So let me get this. Okay, it's loading up.
Could you hear me?
And again, this is beta stuff, so like I may have to restart some of this. Like this, I can see that this.
Can you hear me right now, Connor?
Just give it a second.
Can you hear me now, Connor?
Okay. All right, so I'm going to stop execution. So you can't see it, but I have a physical board that comes with source point that's over to the side right now. I have a USB plugged in that's debugging this over JTAG, which is like a hardware debugging protocol. So what I'm doing is execution is stopped right now on, I'm at the BIOS setting where it says please select boot device, Windows Boot Manager, Wi-Fi, enter setup. So since we're working with VMs, I'm sharing the screen. Can you see this okay?
Yeah, can you hear me, Connor?
Yeah, it's not too bad, I don't think.
Can you hear me, Connor?
Oh, I can't hear you.
Yeah, they can hear me. But...
Did I bomb out? Do I have too many? I could probably turn my VM off, actually, for what I was showing.
If you can hear me, we can hear you totally fine. It's just I don't think you can hear me.
I'm not able to hear you, Steve. Is everything fine though for streaming wise? Can everyone hear me? Okay. So this is source point. I've set a breakpoint on VM launch, which is this opcode, as the name infers, VM launch. And so, like, what happens is I'm on the bootloader stuff right now. So I have a breakpoint set anytime the VM launch opcode is executed, break. So I'm going to press go, and then I'm going to press enter to enter into Windows. The first thing that this is Hyper-V, if I'm not mistaken. You hit go again. This should go into user mode. I forget what context we're in right now, but the third VM launch is actually the entry into the secure kernel. So press go. And what I do is I'm going to hit load current. This loads the symbols for the given virtual address space right here. So you can see down at the bottom in the log. So you can see here, it found the secure kernel, and then you can use this reload command in WinBag. There's these nice built-in macros because there's an interface that allows external debuggers to interface with WinBag. So I can press start, and you can see here, secure kernel, SHVLP VTL1 entry. So what I do is I'm going to hit start WinBag. Give it a second. I'm going to bring the debugger over here. I'm going to zoom in a little bit. All right, I'm going to share the screen over this now. Stop sharing.
Can you hear me yet, Connor?
Screen. All right. So this is actually where execution is at in source point right now. So I paste in the reload command. And now I have all of the symbols present for the secure kernel. So as an example, secure kernel, SK, and then create NT kernel shadow stack. I have all of the code here that we were taking care of earlier. So I'm going to let execution go. And the machine is going to boot up. And then I'm going to set a breakpoint in source point. So present. So I have two windows open, right? I have the source point software and then the actual WinBag software open. So all of the symbols are right here. So you can't see it, but on this screen right here, the machine is loading. So I'm going to go ahead and break. So this is going to land somewhere random because like this is not the same thing as like kernel debugging. This is hardware debugging. Whatever was executing, that's what's executing. You could see for some reason this was when I stopped execution, we were in context of the user mode process. So I have all the symbols right here, and I can Control F and I can search for create NT kernel shadow stack. I can right click and I can set breakpoint. Oh, you can't see this one. Oh well, you can. I promise you can search and in this symbols window over here. So I have a breakpoint set now. I'm gonna hit process, or I'm gonna stop sharing. I'm gonna come over here. The best way to do it is don't press go in source point. Press go in WinBag, at least for my purpose. So the breakpoint is set. You can't see it here, but it's set in source point. I hit go, and it will notify WinBag when it happens. So I'm actively debugging the secure kernel right now. Okay. Here's the call stack that led up to this. I am invoke user mode service, and we can examine some of this stuff. So from the debugging earlier, we know that. Let me put my font. Local. So SKMM create NT kernel shadow stack. The first address should be the target shadow stack. So we know that that's an RCX. This makes sense. This is a page align. But if I view it, it's not mapped in. Makes sense. We just reserve the PTEs. The number of PTEs is the second, or the number of bytes is the second. So 3,000 bytes worth. The third parameter is the flags. So in this case, too, for this was the translation from what was I? Oh, from the user mode thread to kernel mode shadow stack. R9 is the shadow stack type, which 2 is just the translation of what I mentioned earlier. And then on the stack should be the rest. So we know at offset 20 should be the parameters, but the call has already happened. So all of the parameters have been pushed down. So we're actually just going to start at 28. So this is an array of physical frames associated with the shadow stack region. That's what this is that we mentioned earlier. The number of PTEs is the next bytes down, which is we have 1 PTE. We don't worry about this because each of the parameters are 28, 30, 38. So if a D word is used, it's going to align here and fill up the rest of the space so that the next parameter should be down here. This is where the output shadow stack is. Right here. Yeah, exactly. Perfect. All right, so what I'm going to do is I'm going to come back to source point. I'm going to stop sharing the screen. Stop sharing. Share source point. Okay. Have the breakpoints over here. I'm going to delete this breakpoint. I am going to set a I need to use this symbol. Initialize kernel. Initialize shadow. You can't see this because it's like a initialize NT kernel. So I've set a breakpoint there. You can see down here at the bottom. And now I'm not going to press go here. I press it back in WinBag. His WinBag is still broken into. It's not until the command is executed that source point can let WinBag know what's going on. So I'm going to stop sharing my screen here. Sorry about the context switching. WinBag. So I'm going to hit go. So again, here's the call stack that led up to this, create kernel shadow stack, and then the initialization. So if I come back to initialize shadow stack, initialize NT. Okay. So the first parameter should be target region. And this will be a different operation. So this is the hyperspace PTE mapping. So we can see the shadow stack is zeroed out and it's mapped into the secure kernel, in the secure kernel hyperspace. We can see that because these secure kernel, like the stats are from the system region too. So the flags are 8. Okay, so 2 means this is user mode. So what I'm going to do is I am going to set actually that's probably the gist of what I want to show in the secure kernel. So this is how I was able to do a lot of the debugging for the blog post. Was just through this functionality. You can set breakpoints on whatever you'd like. I'm going to stop showing this and come back to source point so I can show. The audience, but you can't. Okay. Oh yeah, you're right. Maybe. Let me try this. Can I hear you now?
Can you hear me now?
No, let me take my headphones off. How about now?
Can you hear me now?
Yeah, I can. I guess my headphones are done. At least the cord on this is done.
Cool. I had to resort to bare minimum.
Was there anyone? Were you trying to get my attention?
Oh no, earlier I was asking you a couple questions and you couldn't hear me, so I thought it was on my end.
Oh, sorry. Yeah, what question? Yeah, go ahead. What questions?
Oh, geez, I have to go back up.
No worries.
Yeah, finish your thoughts and then we'll go back to it.
Okay, so I'm going to come back to source point. Window source point. Because right now we're in context of the VTL1. So if I go to, where was this at? Registers maybe? Yeah, registers. Okay. So registers, there's this VMCS viewer in source point. So it's all of the guest registers, MSRs, or what have you, in here. And if you come down to the bottom, guest SSSP. Now, right now, it's not set because there could be some operation going on. It was just popped off. It might not be updated. Registers. Oh, because we're not in context of Hyper-V. Because Hyper-V is actually the one that's sent from the hypercall. But you can see this is where this VMCX stuff is here. Now, like VM exit and whatnot here, VMCS is going to have the reason for why did a VM exit out of the VM and go into VM root mode, as an example. Or why did we enter into the VM, the reason for it. I don't know if there is a reason for that. But so here's some of the other stuff that you can view. You can view the host states, the actual host information as well. But the guest state is fairly interesting. So that is that. Yeah, that's pretty much the gist of source point. And then the one thing I want to show before I'm done. Oh, perfect. The source point crashed anyway. I'm just turning it off. And then I'm going to plug in my HDMI back. Okay, so I'm going to pull my VM up because I just want to show one last thing of some functionality. Then I promise I'm done. I know I've been talking for a really long time. Sorry.
Nobody's complaining.
Okay, good. All right, I'm going to share. I'm going to start this VM and I'm going to share this. Share screen, window. Okay. Close. All right. Yeah, if there's any questions, let me know. I'm just restarting my actual VM right now so I can show. I just want to show how the token is used once execution reverts back. It's as simple as me setting a break on access breakpoint on the token itself so you can see what's going on.
Yeah, the question I think I was asking you before when the audio wasn't working was if, aside from like going and reading the Windows internals books and jumping into a debugger, what's a good recommendation that you would have for those wanting to get into kernel debugging?
Yep. So the main thing that I would say, and it's kind of, some will say it's counterintuitive. I learned a lot of what I know from debugging, which again, I promise you, if you talk to people like Yarden or Alex, is nothing. Like it's literally nothing. I've seen wizards that just know everything. It's nuts. But for me personally, at least what I got is from the osmosis of learning exploitation. So when you're debugging exploits and whatnot, so what I actually always, again, some people may think it's counterintuitive. I don't just say go out, write your own driver, set breakpoints, do yada yada. I say there's something called Hacks's Extreme Vulnerable Driver online. There are hundreds of walkthroughs online. I would highly recommend starting there. Debugging your exploits. What I did when I first got started is I found Hacks's Extreme Vulnerable Driver write-up. I had my VM and my debugger on one side with the exploits that I just copied from the blog and the blog on the other side. And I step by step just went through. And it's one thing when you tell yourself, oh, that makes sense. You know, I read it and it checks out. Okay, cool. Yeah, I read it. I understand it. No, you don't. You have to do it. That's what I tried to convince myself about browser exploitation. That's where that browser exploit that I did came from. I tried to convince myself, I just won't get into browser exploitation. I'll just read about it. It makes sense. No, you have to do it in order to get there. So I recommend going through Hacks's Extreme Vulnerable Driver, starting with the basic stack buffer overflow on a 32-bit Windows 7 machine. You're going to learn everything about, I wouldn't say interrupts, but how I/O works in the kernel, going from sending user mode input down into kernel mode. Once you're there, I would recommend starting writing your own drivers. On the Microsoft documentation has tons of examples on, like, as an example, you can get notified of every time a process is created from a driver. Write your own driver that processes those notifications. Write your own mini filter. That's scary to a lot of people. Your mini filter is going to be horrible. It'll blue screen the machine 100 times. You know, you're probably never going to release it publicly, like, for people to legitimately use it, but do it. Just go through. There's lots of examples online. And people get this idea in their head, oh, I can't copy code, this, that, and the other. Yeah, give credit when you copy someone's code, but just start by just copying exactly what they have and trying to understand it line by line. Don't try to jump in off the deep end. Take your time with a lot of this stuff. But those are the main things that I recommend to most people is that you kind of have, you have to do it. But people will try to gatekeep and be like, oh, it's this and the other. There are so many blogs out there online. So that's how I got inspired to write blogs. There's lots of stuff out there online that wasn't there 15 years ago and, whatnot. So that's what I recommend.
Yeah, no, that's great points. And also don't be afraid to ask for help. Some people are jerks, like Connor said, gatekeepers. Other people are great, like Connor. He's available to answer all of your questions 24/7. I was kidding.
Oh, well, yeah. No, I'm fine answering because I always, and again, I know I'm going to sound idealistic or like pretentious or whatnot, but I always try to say, especially when you're starting and you have so many questions, people don't realize you don't know what you don't know. And I know that there are some things, yes, you can Google, but there are some things I've asked people for, like, oh yeah, it's not documented. That wasn't documented. I figured out when I was debugging, 3 years ago that you actually have to do this, that, and the other. It's like, I would have never known that had someone not, explained that to me. So that's the other side of it, is that you don't know what you don't know. Now, don't just go spamming questions about like, how do I view the contents of a page table entry? You can Google that. That's something you can find on Google. But, there's other stuff that, explain to me this technique or the other. You might not be able to. So yeah, don't be afraid to ask questions. I try to remember that too, is that ask Jordan and Alex. I still pester them with questions. Andrea, all those people. I try to remember how many people I ask stuff. So when people ask me something, I think you're dumb if you're asking me a question personally, because there's better people than me. But I try to just remember that. So let me do breakpoint, NT, VSL, allocate. All right, RRA. Actually, what I need to do is this. So let me get this out. Kernel options font. Okay. I wanted to go to create or allocate kernel shadow stack. So the argument should be RCX, RDX, R8, R9. Oh. All right, to stack type. Actually, this is the better way to do it. Okay. All right. So this actually is where the shadow stack should be written out to, which is the number of bytes. So when I press P, it's going to go. It's going to execute all that stuff we just talked about before. Oh, luckily I preserved this address. 30. No, I did something wrong. Actually, this is a good time to show. So the R8 register needs to contain 2. Or what does it need to contain? Let me go back to the blog. So the VSL allocate stack. Oh, it should be 0. That's okay. No, 0 is what we want. What you could do is you could do breakpoint, conditional breakpoint, where R8 equals 0, and then say VSL allocate kernel shadow stack. So now every time it hits, R8 is going to be this. You could do this with 2 if you want. I saw one that was used with 2. It may take a while for this breakpoint to hit though. Boom, it's 2. So that's a really useful way, conditional breakpoints in Windows. Okay. R9. All right. All right, here we go. This is the shadow stack. So we can see we didn't have a token set, as I mentioned earlier, with the restore context, FF8. Start user thread, this is the original return address. And this is the actual restore token. So what I'm going to do now is set a break on access. Break on access when 8 bytes are read from this. So when the token gets read, and we can see swap context. So this is the pattern that is used. So the thread is being initialized. The shadow stack is created. After the shadow stack is created, we still have to finish initializing the thread and all that. So once that's done, there's a restore SSP call in NT. And what that does is it accepts a token, a shadow stack token, a restore token. And what it does is it loads it as the current shadow stack. And whatever the previous shadow stack was gets put in its place. So we can see now this token had the 1 set. Why? Because when the restore token is going to be used, it's going to be the active stack. So if we look at the active stack now, it's exactly what now the shadow stack and whatnot is different, but we see this UI start user thread and whatnot. So this is how the context, this is how the system, after the shadow stack and all that is created, brings in the thread on a context to start executing. So if I look back at this address, so this is the shadow, this is the, this was the previous shadow stack value. So we can see what the thread was doing. Now the alignment's off. So this is what the thread was doing. The previous shadow stack, this is what it was up to. Because what restore does is it takes the previous shadow stack to the one that was there at the time the restore happened, and it loads it in. So this is how, see how we're doing a start user thread return? That's what happens when we load back in. So this would have been the process. So what kicked all this off is SBC host created a thread. It had its shadow stack set up. And then eventually when the context swap happened, it swapped into this, into the shadow stack. And that's what happened. KI start user thread, which was the return address we had on the stack to start. So that's pretty much the gist of everything. That's how that token gets used. And again, the reason why we can call these assemblies instructions directly is because the shadow stacks are read only. It doesn't matter if NT can read them, it can't do anything with them. Anyway, so that's pretty much the gist of what I have, Steve. I'm happy to stay on and answer more questions and whatnot, but I kind of just wanted to show, you know, why we need VTL1, why it's important, the functionality, things maybe that vulnerability researchers can look at, such as the caching. Maybe there's something there that can be used. I don't know. I didn't look into it too deeply, and just kind of talk about stuff like this. So, yeah.
Yeah, I'm really glad you showed that last part. That was really cool to see. I don't know how much time that stuff takes. You know, you and probably the developers of Windows who implemented it have looked at it, and maybe 1 or 2 other people.
Yeah, it's interesting. That's what I like a lot about reverse engineering. Is just kind of you know, another person was behind that. You know, that was cool. They chose that pattern or did it that way. So.
Yeah, and I always tell people too, like, you know, it's easy to read the decompiled code and stuff if you know how, but the truth's always in the assembly. So don't always assume that the decompiled code is right too.
Exactly.
Definitely easier to read, not to take as long, but yeah.
Yep.
So no, that was awesome. And I put up a link to Connor's paper already. I'll do that again to his blog here in just a moment. But if you have any questions for Connor that we might have missed, please post them now, because we're at 2 hours and a half. So he's been going for quite a long time, which is super appreciated.
Absolutely. I don't know if I can see any. Oh, I could probably pull up YouTube online. There's probably from other places though too.
Yeah, they'll be coming in from LinkedIn and stuff too. Let me look up and see if I missed any. Somebody just typed something. Nope. Cool to see in action. Thank you. I think Connor covered that one already from the cyber, just asking about tips and tricks. One thing I say too, like Connor was saying, grabbing exploits and debugging them and working through them. I always like to say places like exploit database, exploit-db.com has all these vulnerable applications. You don't want to put them on your regular computer on VMs, of course. And next to it is the exploit code. So you can kind of filter what category of exploits you're looking for. And then I always recommend don't look at the answer. You know, if you can treat it as a 0 day, even though it's not, try to, since you know there's a bug in that application, you can try to find it yourself. And if you can't find it through fuzzing or whatever, then go and look at the answer, but then still go back through and try to work through exploiting it yourself. And there's like a never ending supply of practice ones there. And they range from simple stuff like stack buffer overflows all the way up to like use after free and type confusion and other things. Let's see here. Candy saying 19 years old. You're also 19. I don't think Connor's 19 anymore, but
no, I'm 27.
But yeah, he's only like a couple years younger than me, right? No, I'm just kidding. He says, for wanting to start in this field, is it good to dedicate the next 5 years? I guess the question is more around how long do you think it would take to get up to a level where you can see some results? I mean, it's different for everybody, but what are your thoughts?
Yeah. I would say definitely, like, if you have a hard time frame of, I'm going to spend the next 5 years doing this, because it's not just about the exploitation. Like I said earlier, a lot of this is 90% reversing, understanding your target, how it works and whatnot. And the other 10% is the exploitation, where you read the papers on how to spray, how to do techniques like rob, that sort of thing. Those concepts directly tie to other things like systems programming or other valuable fields. I am wholly convinced people, and again, I shouldn't say this. This is my opinion. I mean, I hate saying my opinion, but I feel strongly about this. I don't feel that people view that kind of stuff as glorious anymore. The systems programming, the file system development, the low-level stuff that's not offensive related. So I'm talking like triaging crash dumps, you know, I want to work at Microsoft on the kernel team and write features and that sort of thing. That doesn't seem to be the route that a lot of people that I know go down. A lot more people are interested in the exploitation route. But by nature of being involved in exploitation and doing all these things, a lot of the skills directly tie over. Your debugging skills, your knowledge of the operating system. That's what it comes down to a lot. A lot of it is not knowing C and all this stuff. It's knowing, okay, when the processor is at this URL, I know that if I access page memory, that I shouldn't be doing that, because the page fault handler can't be scheduled because we're at a high URL, and therefore if I incur page fault, I'm going to blue screen. That's not code. That's Windows internals knowledge. And that's a lot of the stuff that is directly applicable to being a systems programmer or doing all that. So I would say, spend the next 5 years doing it. Even if it's pure exploitation, if you're doing Windows stuff, you're going to be reading the Windows internals book. You're going to be coming across the same type of stuff that is used. Alex's talks, Yarden's talks, a bunch of various other stuff. And by nature of that, you're going to have, I think, a broader skill set than you realize, because you're going to have spent a lot of time in the debugger. You're going to have spent a lot of time understanding the Windows internals, user mode, kernel mode, patterns that are used, that sort of thing. So I would definitely say go for it. I think that we all have this kind of existential crisis, vulnerability researchers alike. One day it's, man, it's getting too tough. Then the next day you see, there was still a stack-based buffer overflow here. And it's like, maybe it's not done yet. So I think it's going to be around for a while. Think about how deeply embedded C is in everything. We're not going to wake up tomorrow and Windows is going to be rewritten in Rust. Parts of it are being rewritten in Rust as we speak. It will continue to improve, but that's not going to be something that happens overnight. And so definitely continue.
Yeah, I mean, Windows has been around, you're looking over 35 years now. So there's so much, like back in the original days, you had POSIX and OS2 and all these different, and no one really knew who was going to win the war and like who gets the market share of operating system for the end users. So there was so much interoperability and compatibility built into it from the beginning. And there's so many just old legacy dependencies and still new development happening in C++ for a lot of your big applications. So to be able to change that stuff over would take a massive amount of time and work.
Oh yeah, absolutely.
And there's also a lot more out there besides just the Windows OS. You've got all the IoT stuff. You've got all these microcontrollers, and you've got different operating systems and mobile and everything else. And of course, AI and that technology and blockchain, smart contract. There's so much you can focus on too.
Yep, absolutely.
Cool. Well, I don't see any more questions popping up, but thank you so much. This is a great stream. Very, very useful information. It's going to be obviously on YouTube after this for folks to watch afterward. Coming up, we've got a couple streams. Things like looking at deobfuscating Golang malware, which I think is a pretty cool topic. Looking at more Web3 stuff here and there. Another topic on looking at the anti-forensics and kind of DFIR perspective. So even though we're trying to cover our tracks, we're still leaving artifacts behind. And how are these really smart, deeper people able to do that analysis and still try to figure out what happened? And can we use that knowledge to obviously hide a little bit better? So some cool stuff coming up. But otherwise, hopefully someday again in the future, we'll have Connor on, because always a great guest. But otherwise, have a great weekend, everybody, and we will see you next week.
See y'all.